We're going to be making a series of slides now to help you with factoring by grouping and factoring completely, which essentially just means keep factoring until you can't factor anymore. I'm going to start with number 5, as listed here on the slide, x to the third plus 7x squared minus 9x minus 63. This problem right here. And the first thing we've done is taken the x to the third plus 7x squared and group that together, followed by the negative 9x minus 63 and group that together, and they're adjoined using addition. And the reason we're using addition is 7x squared minus 9x as listed above is the same as saying 7x squared plus a negative 9x. So it's okay to group them in two separate sets of parentheses. We're just portioning them off. Now when we look at this first group here, the common monomial that we can pull out is x squared. When you divide x to the third divided by x squared, you get x. And 7x squared, when you factor out an x squared, leaves you with 7. On the right side, we pulled out a negative 9, and negative 9x divided by negative 9 is positive x. The negative 63 turns into a positive 7. From there, what we want to do is we want to take a look now and see some of the common pieces that are in both sets of terms. In the front set, we have the x plus 7 adjoined by the x squared by multiplication. And in the second set, again, x plus 7 adjoined to the negative 9 by multiplication. Because these terms here and these terms here happen to be attached by multiplication, it's okay to factor out again the common term, which happens to be written in white. And so what we're going to do is we're going to factor out the x plus 7. Now in this first set, when we factor out the x plus 7, what's left is the x squared term, which comes right here. And when we factor out the x plus 7 out of our second set here, what we're left with is the negative 9, which drops down right here. And so after we factored out the x plus 7, we have it out front, we have our two remaining terms, x squared minus 9. We can't stop at this point. Now, we've used factoring by grouping to get us to this point, but now the factoring completely sort of kicks in, and this isn't factored completely. The x squared minus 9 is the difference of perfect squares, which factors quite nicely into x plus 3 times x minus 3, and the x plus 7 is out in front. Remember that if we take this final answer here and we multiplied all three terms, what we should get is the original problem that we started with. Now we can say that this polynomial, x to the third plus 7x squared minus 9x minus 63, has been factored completely. Our next example is going to be number 6. 16g to the fourth minus 625. This problem is the difference of perfect squares. 16g to the fourth is a perfect square. 4g squared times 4g squared would give you 16g to the fourth. And 625 is a perfect square. Square root of 625 is 25. So this factors quite nicely into 4g squared plus 25 times 4g squared minus 25. Now all we got to do is just make sure that we can't factor any further. The 4g squared plus 25, we can't factor out any common monomial out of there. But the 4g squared minus 25 is the difference of perfect squares yet again, leaving us with 2g plus 5 and 2g minus 5. Again, before I walk away from this problem, I just want to make sure that each of the three terms doesn't have any kind of common monomial that can be factored out. Otherwise, we're all set. Moving on to number 7. Looking at number 7, I can quickly see that I can factor out a monomial of 4 for a number and t squared for a variable, leaving us with 4t to the sixth. When I factor out a 4t squared, it gives me a t to the fourth. Negative 20t to the fourth, when I factor out a 4t squared, leaves me with a negative 5t squared. And positive 24t to the second, factored out by 4t squared, leaves me with a positive 6. And now I'm going to factor out the remaining trinomial here. So not forgetting, we're taking care to make sure that we bring down the 4t squared. I'm left with a t to the fourth minus 5t squared plus 6, which gives us t squared and t squared. Because 6 is positive, I know that both signs right now are either positive, positive, negative, negative, and the sign right here tells me which one it is. So they are both negative. Two numbers that multiply to give me 6 and add up to 5 are 2 and 3. Now, all I want to make sure, as always, is looking to make sure that nothing else is factored or factorable any further. Otherwise, we are factored completely. T squared minus 2, well, that's a difference, but it's not the difference of perfect squares because 2 is not a perfect square, and t squared minus 3 is not the difference of perfect squares either. So as far as factoring is concerned, we are all set. The next problem asked me to focus on the real solutions of the equation 3x to the fifth plus 15x equals 18x to the third. Since I'm going to solve this by factoring, I need to get everything set equal to 0. So my first move will be to rearrange things by subtracting 18x to the third from both sides, putting it on the left side. Because it's written in powers of descending order, I chose to put the minus 18x to the third in the middle here because it's x to the fifth, x to the third, and x to the first. Now we factor out our monomial, 3, and the most amount of x's I could pull out is just x to the first, leaving us with x to the fourth minus 6x squared plus 5 equals 0. And we can continue to factor. Our x to the fourth breaks into x squared and x squared. And since it's a positive 5 at the end here, I know that both of my signs are going to be the same. Since it's a negative 6x squared, that means that both of these are negatives. Two numbers that multiply to 5 and add up to 6. Pretty simple, 5 and 1. And so we have 3x, x squared minus 5. And then the x squared is the difference of perfect squares. So we have x plus 1 and x minus 1 equals 0. Now we're going to take all of our factors, set them equal to 0. So we got 3x equals 0. X squared minus 5 equals 0. X plus 1 equals 0. And x minus 1 equals 0. And for our final answers, we have x is equal to 0 from the first set, plus or minus radical 5 from the second set, negative 1 from this set, and positive 1 from the last set. So which of our answers reflect this response? And I believe we're looking at choice D. Our last problem is going to come from the book Problems number 38. And again, we're going to focus on finding real number solutions. I've already taken the liberty of taking the negative 36 and adding it to both sides and setting this equal to 0. From here, I'm going to factor out a 5b squared, leaving me inside the parentheses with a b plus 3. Then I'm going to factor out a positive 12 out of the next set, leaving me again with a b plus 3 equals 0. When we factor the b plus 3 out to the front here, that's going to leave me with 5b squared plus 12, all of this equal to 0. Now I'm going to take my terms, my factors rather, and set them equal to 0 and solve. My first real solution is b equals negative 3. When I take the 5b squared plus 12 equaling 0, I'm going to end up subtracting 12 from both sides. And you're going to see pretty quickly that when we divide by 5 and divide by 5, we get b squared equals negative 12 fifths. And when I take the square root of both sides, this is going to yield me an imaginary answer, which I am now just going to toss out this whole thing because it's not real.